Hello, my name is David Moore. The following is a video series that provides a very complete guide to RGB and pixel-based devices used in residential holiday displays. This video should provide the layperson with the information necessary to make informed decisions on the purchase of pixels, controllers, hardware, and software. We will not, though, be providing purchasing recommendations for any of the items featured in this video series. Using the information provided in these videos, you should be able to work towards making an educated decision on the purchase of your equipment. Every effort has been made to keep a level playing field on the reporting of information provided. Please keep in mind that due to the number of changes occurring currently within the industry, both on the commercial and the do-it-yourself side, any of this information is subject to change at any time. Pixel level control of lighting is not a simple process. Yes, it can be viewed as a simple process when broken down into many of its sub-elements, but in total, pixels are fairly complex when put into the context of a traditional display. While purchasing from a commercial vendor or purchasing a standardized do-it-yourself system may cut down on this complexity, a fair number of decisions still need to be made by the end consumer of the product. If, after reviewing this information, you still feel as you do not have a complete grasp on all of this information, please be sure to post your questions and get feedback. Investing in RGB pixels is just that, an investment. And some of these investments do lock you into a given system. It is highly recommended for you to be aware of all the advantages and disadvantages of a system you choose before purchase. What is RGB? RGB is an acronym for red, green, blue. Using these three primary colors, we're able to mix and create any secondary color we need. For example, if we need purple, yellow, pink, those three primary colors can be mixed together to perform those secondary colors. Now, one of the keys to this is that those LEDs have to be very close. Those three colors need to be able to be viewed as one. If you look at your TV, you'll see that all three colors within your TV exist in a very small space. When viewed from a distance, those colors seem to mix together to create one single color. So, that is what RGB is. It's simply three colors close enough together to have the appearance that they are one color. Nearly all RGB devices are comprised of three different types of LEDs. LEDs are light-emitting diodes. The most common of these LEDs is one that most people are probably not familiar with. This is the 50-50. 50-50 stands for 5 millimeters by 5 millimeters. Within this small little chip are three individual LEDs, one containing red, blue, and green. Those are then mounted into a larger device, which in this particular case contains three 50-50 LEDs. These have the advantage of being very wide angle. They can be viewed at 120 degrees. They're very flat, and they have excellent color mixing because the LEDs are so close together. Now, the second most popular type of LED is the 8 millimeter. These are typically found in pixel nodes. Within this individual pixel, we have three LEDs. So there is a red, blue, and green light inside of this. Combined with the diffuser allows it to produce all the different secondary colors. Now the next, but not common, is the 5 millimeter. The 5 millimeter has separate individual LEDs. These look like LEDs you might see on any type of device or product, and they're individually separated. Now, because they're slightly separated, that means up close they don't have good color mixing. But from afar, you can't tell that much. So these tend to be the most economical. These are used because they have a more traditional LED node-looking effect. And these are used because they're flat and they also mount very easily without any through-hole components. Now, what we have is three major categories that those different types of LEDs mount into. Those are modules, strip, and nodes. The first of modules is probably the most varied group. For example, we have here a RGB module. In this module, which is rounds for ears for mounting, a diffused cover. If I pull off this cap, you can see that it has three 50-50 LEDs inside. Another type of module, here's a larger version of that type of module. It has a much larger side profile, a slightly different mounting, and different wiring. We have other types of modules. In this particular case, here's a non-diffused module. This module is comprised of four 50-50 LEDs in a square that contains a clear potting material. We have other types of squares. For example, here, this is a stainless steel square with a little hole in the center for screw. Three 50-50 LEDs mounted in there. Connected with wire here, and of course differing levels of distance allow you to adjust for those different needs. We also have rectangular modules. A common size is about 3 inches, and in this particular case we have a module that has three 50-50s in it. These are sealed, epoxy also. There are tabs here mounted on the side, but often they have the tabs mounted on the ends. Another type of rectangular module here is this one. This one contains the 5mm by 5mm LEDs. These are very inexpensive, but of course they lack the high level of color mixing that you do have within a 50-50 type module. Now, the next major grouping is strip. Now, strip, generally speaking, is flexible. It has several characteristics. First is, it is flexible. It can be bent. You can see it can be bent in this way, but it does not bend this way. It is a circuit board with almost always 50-50 LEDs. They vary in distance. For example, you can see that these are, in this particular case, 3 per section, and each section is about 100 millimeters, or about 3.5 inches. Within strip, most often you can cut it, and there's an indicator here for cutting it here or here. And these little black spots are where you're able to resolder wires. So if you needed to go around a corner and make a 90-degree corner, you could cut that, splice in a small section of wire, and then continue off in a different direction. Now, several things on strip. There are 3 major categories of protection. Because this is a circuit board, it needs to be protected, and these are electronic components. One of the types of protection is a clear silicone coating that's actually glued on or part of the circuit board, and it may be hard to see this, but this is actually a solid item. Now, that is very waterproof, but it does make it a little bit harder to get down into the splicing. So if you have to do a lot of splicing, sometimes it can be a little more complicated. The other type is a boot only. You can see here, there's the strip. It has a adhesive on it that allows you to mount it to something. That is then slid into a boot. That allows it to have some play so that if you mount this boot to something with this strip or this adhesive here, it does allow it to have some play. So if you have something that's flexible and you're worried about breaking the circuit board, generally the boot would be a better choice because it does allow free movement of the circuit board inside the boot. Now, the most durable type is one that combines both of these. And this is that type right here. This is a clear boot, and you can see that it's fairly thick. It has the silicone and the boot. So it's a very durable type strip. Now, strip does come in 2 different variations in terms of density of pixels most often. What we can see here is that we have 1, 2, 3, and here we just have 1, 2. So this has an extra pixel or an extra LED, 50/50 LED in between each one. This is 30 50/50s per meter. So for every meter, it has 30. This has 60 50/50s per meter. And of course, obviously, this is going to be quite a bit brighter and obviously more expensive too. Now, also things to be aware of, there are different kinds of backings. So for example, we can see here, we have 3 different kinds of strip. This has a very dark backing, and it doesn't reflect light as well as the white backed particular strip. And the same applies to these. Is not as reflective as the white. Now, a slightly hybrid version of the strip is strip mounted to a solid carrier or a channel. And in this particular case, you can see that there are some little mounting tabs. And this is simply 50/50s on a strip that are siliconed or epoxied into this channel. Very rigid. It ensures that there's no bending, which could damage the devices. The disadvantages are that these generally are more expensive, harder to ship, and do limit you on the distance. It's not as easy to simply just cut these in different sections where you need them. They do have uses, but often if you need to mount these, you can take general regular strip and just zip tie it to PVC pipe or some other harder substrate. Now, the third type of pixel, or RGB light, is a pixel. In this particular case, we have one that looks very close to what you are familiar with traditional LED lights. It has a single light at the top, which is 8mm LED. In this particular case, it is individually pixel controlled, so there's a computer chip in here. It has some wire between these. This distance of wire between each pixel can vary. These nodes generally just have one LED. You can mount these. These have a little boss that you can mount these in. Pop these into a panel, and you can use them free-form. Now, one of the common problems with these particular types of devices is that there is often a gap between these particular nodes, and that can allow water ingress into the nodes. In these particular ones, you can see that there's quite a bit of gap in here, and as the water comes down the line, it can get in there and short-circuit the board. So quality concerns are always an issue for these kinds of devices. Not so much on these types or on the strips, because these are usually 100% sealed with some sort of clear epoxy or plastic. Okay, now that we have talked about the different types of LEDs and the different types of devices that they are mounted into, let's talk about the 2 major categories of RGB. Now, these 2 different categories are separate in the way that they're run. They share some common traits, but they are very different in the way that they're set up and designed. Now, basic RGB is the closest thing that you have to your traditional light strings. In a traditional display, we have a controller, and you might have super strings with red, blue, and green lights allowing you to control all those different colors. Now, how that differs is that you would have an AC-based controller with AC power in and AC power out to LED or incandescent strings. But in RGB Basic, what we have is we have a DC controller and we have RGB lights. Now, the difference between your traditional strings and RGB lights here are that, of course, as I mentioned before, the RGB allows you to color mix these. So because the lights are so close together, we can control them to make them red, blue, or green. Now, these are different from your traditional displays because these are DC, and as such, we have 4 individual wires. We have a red, blue, and green wire, and we have a shared positive or common anode. Now, the most common type of basic RGB lighting is common anode. That means that there's one positive input and three negatives. Then on your controller, if it is RGB based, you'll have one connection for positive out, and then you'll have three negatives that control the individual colors. Now, the type of controller you use can vary. We can have controllers as small as this. This is a 3-channel DMX controller. We have them in little strips, a 3-channel DMX controller. We have them in boxes, a 3-channel DMX controller. We have them without boxes and screw terminals, another 3-channel DMX controller. Again, the commonality here is you have 4 wires out, you have some signal put in, and power input. Now, why would you want to use basic RGB? Well, there are some devices that work best with basic RGB. For example, if you have a standalone device such as a CoroStar or a Snowman or some other device that just needs to be entirely lit up in a particular color, basic RGB works well. You don't need to control the individual lights within that, which is RGB pixels. So basic RGB is a good, less expensive, less complicated, and it of course requires less channels because I'm able to control many of these lights off of just 3 channels, and it's a good alternative to pixels. RGB pixels, which also can be referred to by a variety of other names such as intelligent, nodes, or digital, such as digital strip, all have one thing in common. All of them are discretely controllable devices. So, in the case of these pixel nodes, we have a computer chip in each individual pixel node that allows us to control this one LED. This can be controlled separately from this particular node. Or, if we have modules, that means that this entire module, which contains 3 50/50s, can be controlled. So there are 3 channels here. The 3 channels would make all of these red, all these green, or all of these blue. The same here. Again, just physical differences in the number of LEDs. 4 LEDs, I can make them all red, all blue, or all green, or mix them to make any other color. It also applies to strip. There's a computer chip on each strip. Each section of strip, which is usually about 100 millimeters long, is individually a pixel. So these 3 LEDs, along with this computer chip, comprise 1 pixel or 3 channels of channels within your particular sequencing software. Now, one of the things that may confuse you is that pixels have no addresses. So if you just take these pixels out of the box, there is no way to set an address. How a pixel gets its address is from the distance from the controller. So we would have a controller that is hooked up to this. So for example, in this case, we have a very small controller, and it is hooked up to this pixel module. And you can see the computer chip in there. Now, what would happen is that if I hook these up, this would become the first pixel, that would become the second pixel, that would become the third pixel, fourth, and so on. So, they are generally physically selected as being 1, 2, 3, 4, and so on, all down the line. Now, how does that actually map over into your software? So, this may physically, in the software of the controller, be pixel number 1, but it actually may be channel 200, 201, 202, and this is 203, 204, 205, again, because we have 3 channels for each individual pixel. What happens is that the entire chunk of data for all of the pixels that are in this particular string will be sent down the line from the controller. Think of it as Lego bricks stacked on top of each other. The first one, this nodule here, or this pixel here, will take the first brick off and say, that's my data. This particular pixel then thinks it's the first one. It takes off the first chunk of data, then sends it down the line to the next pixel. This pixel takes off its piece, and then so on. So the distance from the start of the controller is what determines the order of these pixels. Now, there's physical pixels and their addressing, so this is 1, 2, 3. But again, you may have logical addressing that is applied inside the controller itself. So in your controller, you're going to tell it that pixel 1 physically hooked up to this particular controller is DMX or LOR channel 100, 102, 103. Again, RGB, we've got 3 channels. And then this becomes 104, 105, 106. Now, we will talk about some other interesting ways to address them. We can separate the physical addressing from the logical addressing, and we could have them go backwards. We could make this 100, 101, 102, 104, 105, and 106. So, the thing to be aware of is that each one of these pixels is individually controlled. Now, several things to be aware of with these is that each individual pixel has an in and an out, and there is regeneration of the data. There is a distance limit between each one of these pixels. That varies based upon the particular chip you're using. A typical rule of thumb might be anywhere from 10 to 20 feet distance between these. And we'll talk about later some of the issues that can arise. For example, if you have your controllers way away from your first pixel, how do you make sure that the signal gets to the first pixel without getting corrupted? Now, as it goes to each pixel, that controller then picks up the signal, regenerates it, and sends it on to the next pixel. So, in general, assuming you don't have large distances between each one of these pixels, you can send the data for extremely long distances. What is generally the limit, and we will talk about this in depth later, is the power. You can only send so much power down these thin lines before it becomes an issue.
Now let's look over at a controller and its configuration program. Your controller would probably have a similar type application either on the PC or it would be web-based. And in this application, it allows you to configure the physical pixels and the logical addressing of those pixels, along with other technical details. So this particular controller, the TP3244, has 4 outputs. It can put out data on 4 different sections. It can put out signals for 4 different kinds of chips, and we will talk about those chips later. Now, one of the first things we need to do is define how many pixels. Now, this is not channels, but pixels. So if we have 20 physical pixels, that's whether they're modules, strip, nodes, we would need to have a matching number of pixels to match the software. If you do not put the exact number, either one, you'll end up with less data output. So if you put 18 in here and you had 20 physical pixels, you're going to end up with 2 pixels at the end that either don't come on, don't act correctly, they may flash randomly. So you always want to make sure that the number of physical pixels matches up to what is configured in the controller. So we've got 20 here. Now, the second thing we need to do is set the start channel. Now, this particular controller works off of DMX, which is most common on many controllers. We need to map over exactly which channel will be used. So if we want pixel number 1 to be channels 1, 2, and 3, we would need to put in here the start channel of 1. That means that pixel 1 will be channels 1, 2, and 3, and the second pixel will become 4, 5, 6. Now, you can start that in the middle. So we could do 100. So let's say you've got some devices that are using up channels 1 through 99. You want to start at 100. You can start at 100 here, and that would mean the first pixel would be channels 100, 101, and 102. The second pixel would be 103, 104, 105. Now, the other thing that we would configure here is the protocol. There are different kinds of chips, and we will talk about those later, but we would select the type of protocol that is output. Some manufacturers will not have this because they have a standard type of chip that works with their particular hardware. Some are multi-protocol. We also may have a universe. This universe has to do with which section of data. This was related to DMX, and we'll talk about that later. Now, we also may have reverse order. So, for example, using the example of a start channel of 1 and a number of pixels is 20, that means that we can take 20 times 3 and we end up with 60 total channels. If I reverse the order, and most controllers have this option, what that allows it to do is that the first physical pixel closest to the controller will actually be pixel number 60. So it'll be our channel number 60, which is channel 60, 59, 58. The second physical pixel would be 57, 56, and 55. So there are times where you want to actually run the pixels backwards. So for example, if you had a controller in the middle of 2 pixels, you might want to run the left side of the pixels backwards or in reverse, and then run the right side of the pixels in forward, which would make them 1 through whatever.
To expand on reverse or split addressing, if you did have a controller that was located in between this string, and you wanted this particular pixel to be pixel number 20, and then the next one in line 19, so they were going backwards, which is reverse, you can usually configure that within most controllers. This would then become pixel 1, 2, on a different output. Now, some other unique things that you may have within a particular controller is dead node or repeating node skipping. What this allows is if you have a long distance between your controller and its output and the first pixel, you may have such a distance, such as 20 or 30 or 40 feet, that you need it to be able to reproduce the signal. As I mentioned, each one of these pixels reproduces a signal, and they can only go a certain distance, and that varies based upon the particular kinds of chip and wire and a variety of other factors. So there may be, if you imagine that this were a long distance between these particular nodes, what we may have is this node skipping. We just want it to reproduce the signal. We don't want it to be counted as a node. We want it to be ignored. So imagine that we have 20 feet, and then the first pixel is our first addressed pixel. In your hardware configuration, you would say, I have one dead or skipping node. This is simply just there to repeat the signal. It won't be used, it's just to repeat the signal to get it on to the next one. So it's a useful feature if you especially have a centralized approach for controllers. Now, controllers also have built-in hardware-based macros. Some of these are done to overcome limitations in software, which exists today in sequencing software. Some of them just provide additional functionality. One of those is phantom channels. So, for example, let's say that you really just want to treat your pixels as if they are one long string of basic RGB devices. So you really don't care about controlling them individually. You want all of them to turn red, all of them to turn green, or all of them to turn blue. Within your controller, you can set up a phantom channel that says, okay, channel number 1 is red, channel number 2 is green, and channel number 3 is blue. And it will actually tell each one of these, even though they're individually addressable, to turn on to a particular color. What this does, of course, allows you to only use 3 channels, which is great if you have software that is limited or you have a problem with outputting huge amounts of data that is required, and we will talk about that later, to the pixels. Some also allow something called grouping. Now, grouping allows you to simply put them in either sections. For example, I can make these 2 a group, and in the software I would say 2 nodes or pixels become 1 pixel, or I might have 3, or I might have 4. So when I turn them on, when I say channel number 1 turns on 4 pixels all at once. Then turns on channel 2, might be green. Usually the number is configurable, and that allows you to reduce the channel count but still have a level of controllability. So it's basically taking what is very controllable as individual pixels and grouping them together. Now, we also might have something called zigzag. You may have a matrix in where you have gone back and forth to create a matrix. And that can create some issues if your software doesn't understand how these are laid out. You may want them to be oriented more like 1, 2, 3, 4, 5, 6, any more grid pattern. But physical addressing would dictate that their wire direction addresses them. So this would be 1, 2, 3, 4, 5, 6, 7, 8. And that may not be what you want. Zigzag pattern allows you to adjust for that. Again, this particular case with zigzag, you would have ideally software that would better support that. And you could make this 1, 2, 3, 4, and the software would understand the physical pattern of those. Also, you may have chases or fades. You may have an option that says allowing you to define a certain number of pixels to be a chase pattern. So you call a particular channel that says channel number 1 is a red chase from left to right. Those are on certain controllers. Again, that is kind of a stopgap for software. It allows you to simply perform complex operations with very few channels.